Okay, so we are into the types of machines, and we are going to treat the different types of machines we have. There are so many of them. So we have, first one, we have a lever. So we are going to treat lever. We have our lever, we have pulley, the pulley system. We also, that is tackle and pulley. So we have tackle and pulley system. We also have screw jack. We have screw jack. We have gear system. We have inclined plane. Inclined plane. Which other one is normally asked? We also have hydraulic press. Hydraulic press, or you call it hydraulic pump. It doesn't matter. Which other one? We have wedge. We have wedge. What else? So what we have here are the types of machines, and in each machine here, from lever to wedge, if I still remember another one, I will add. Now, these are the types of machines we have. In each one, we are going to be treating the velocity ratios in each one. So we have the lever, the pulley system, screw jack, gear system, inclined plane, hydraulic press, wedge, and so on and so forth. So other ones, we are going to treat them in each one, the velocity ratio. So quickly, we are going to enter lever. So let's know what a lever is and what we use levers to do. Okay, now we have the types of lever. A lever, by this diagram, simply means any device that you can, I think here we normally call it a juggler, for instance, when we are staying in primary school. So if you can, someone sits here and the person can lift this person. Remember, there's always something inside or between them. That is called a fulcrum. A fulcrum is also called a pivot that's used without this load, is already standing. It can be in equilibrium without the load and the effort. But once a load is already on it, it will fall one place. So you need an effort to lift that particular load. Any type of that design is what you call a lever. So we have different types of levers, or you can say classes of levers, or orders of levers. So the first one is called the first order lever, or you say the first class levers. So how do we know that a particular lever is a first class? By the position of the fulcrum. So when the fulcrum is between the load and the effort, when the fulcrum, as you can see from the diagram, when the fulcrum is between the load and the effort, it doesn't matter the position of the load and the effort. Here can be the load, while here can be the effort. It doesn't matter. What matters is that the fulcrum is between the load and the effort. So in real life, examples of this first class lever is claw hammer. If you want to use the claw hammer, you will find out that you are placing your load at the mouth. This side you are holding the hammer, while there is a little knot between them. That little knot serves as the what? The pivot or the fulcrum. So a claw hammer is a first class lever. Crowbar is also a first class lever. A pincer, you also use it to pierce ears and so on and so forth. You find out that the load is attached at the mouth. While you apply an effort, there's always a round something holding it in between, serving as the fulcrum, so that it can be able to what? Turn. So we have, anytime you have something like that, a fulcrum between. This is called a first class. Your scissors, a pair of scissors is also an example of a first class. They also have pliers. Please note these peculiar examples. If JAM, Waec, or posterior, they won't ask you questions, they will still pick from these examples. They will not leave any of these examples. So know them very well. Claw hammer, crowbar, pincers, a pair of scissors, pliers. You can also, furthermore, to know when we have so many types of first class lever, provided that the fulcrum is between the load and the effort, or you say effort, load. It doesn't matter. So we go back to another class. We have three classes. The first class, the next one is the second class. So the second class lever is anytime you have the load any device, any type of lever you see the load between the fulcrum and the effort. Between the fulcrum, you can see the load here, is between the fulcrum and the effort. As I'm even talking to this, your mind should be telling you one of the machines. For instance, we have what? A wheelbarrow. That's a popular one, or the nutcracker. A wheelbarrow, you place your load in between your effort, where you push it, and the tire. The tire is the what? The fulcrum. So you have where you apply your load, your effort, the load is placed between. So anytime the load is placed between the fulcrum and the effort, that type of lever is called a second class lever. So the difference in these classes of lever is the position. The positions of the what? The fulcrum. That's what the difference. The position or the fulcrum. Another thing they normally ask you in your posterior knee is this. Note this. They will tell you in which of these classes of lever is the velocity ratio and mechanical advantage greater than 1. That is in second class. Please note that. So in second class lever, the velocity ratio and mechanical advantage are always greater than 1. Unlike the next one we are going to enter. So note that examples of a second class lever or second class levers, nutcracker and the wheelbarrow. So we'll move over to the next one now. Okay, now we have the third class other lever here. Now in third class other lever, just the shift in the effort this time around. As you can see, the effort is between the fulcrum and the load. So once the effort is between the fulcrum and the load, you call that a third class lever. A third class lever. Now we have examples of that on the board. We have tongs, different types of tongs. We have forearms. Your forearms. You also have your knife. The knife, before you cut, you know where your table knife, to be precise. We have our table knife. Then we have fishing rods. Then the forceps. So if you want to do anything now, watch. This is where our effort lies. If you want to carry something here, this is your fulcrum. As you can see, this is where everything happens. This is your fulcrum. Now, anything you place here, your effort is working here. Anything you want to lift now, you are applying, this is where the effort is coming from. While you are putting something here to lift it, a load, this is your fulcrum. So this is an example. Your forearm is an example of what we call what? A third class lever. Now, another thing you should know under third class is that the mechanical advantage and the velocity ratio are less than 1. Please note these important things. The mechanical advantage and velocity ratio are less than 1. Actually, this is coming from the principle governing lever in general. So what is the principle governing lever? The principle of lever uses the principle of moments. So if you missed our class, a moment, you can always visit this if you do blog. Now, let me quickly show you how this thing works. This is what we have. This is the first class lever. So we have our load, we have efforts. This is the fulcrum. Now watch. This is for the first class. You are not going to see this in any textbook you are using, so be very careful here. Now, from here, you always measure a moment from any line perpendicular from the line of action of the force. So the line of action of this force is the pivot. So this is the point. Now we are taking our moment at F, which means every distance will be read from F. So from here, the perpendicular distance, small e, is the distance, is the perpendicular distance, you can see, is the distance moved by what? Effort. Now the distance moved by load, let's call it small l, from here to this point. By principle of moment, we are told that clockwise moment, anti-clockwise moment is equal to clockwise moment. So we have moment is force times distance. So we have effort times distance moved by effort is equal to load times distance moved by load. Now, if I cross multiply, I want this young man to come to this point and this young man to come to this point. So what is going on now? You can see, let this come here. We have F, distance moved by effort divided by distance moved by load is equal to load over effort. So if I cross multiply this, I'll get back this original equation. Now, what are you seeing now? Distance moved by effort over distance moved by load is called velocity ratio. Load over effort is called mechanical advantage. So in first class lever, as you can see, the velocity ratio is equal to mechanical advantage. The velocity ratio is equal to the mechanical what? Advantage. Now, let's look at the second class. So always know this, the principle of moment. So lever uses the principle of moment. So if we look at the second class, in second class we have that the load is between the fulcrum. The load is between the fulcrum. Now we are not taking moments here. So we have here, from here to be distance moved by load. While from this point to this point is the distance moved by effort. So what do we have now? Now we can see that the distance from here to here moved by effort is very large. You can see that from here to here, the distance moved by effort is very large. So if we write out the principle of moment, you have that load is equal to E times this. Now, from here, this distance is very large. So because it's very large, as you can see from here to here, it will always be greater than 1. No matter what you solve in practical aspect of this, no matter what you solve, you find out that this velocity ratio, let's check, we have load over effort is equal to distance moved by this divided by this. So have you seen that this is bigger from our diagram? This is bigger than this. So this divided by this will always be greater than 1. No matter what you do, no matter what the calculation is, this divided by this will always be greater than 1. This divided by this will always be greater than 1. Why? In the actual sense, load is always greater than effort, provided machine is consigned. So once this divided by it will always be greater than 1. Same thing here. So that's why in second class, the mechanical advantage and this is always greater than 1 from our diagram, as you can see. Okay. If you go to third class, in third class we have that our effort is between our load and the fulcrum. Our effort is between our load and the fulcrum. So distance moved by effort from here is this. Distance moved by load is this, small l. So if we still do what we have, following the principle of moment, load over effort, so we have E over L is equal to L over E. What is going on from our diagram? As we can see, the distance moved by load is now bigger. So since the distance moved by load is bigger, which is this distance moved by load is bigger than this. If you say that this is 20 Newton, distance moved by effort is 20 cm. Automatically, distance moved by load will be greater. So if we say that from here to this point is 20, and let's say that this is a uniform something, that the total is 100. From here to here, we give us 100. As you can see, if you divide this 100 cm, it is less than 1. Same thing goes here. So always know that in third class, the mechanical advantage and the velocity ratio are less than 1. While in second class, they are greater than 1. Okay, this is all we need to know about lever. Let's solve an exercise concerning that.